In this video, we're going to go through what wave speed is, what factors can affect wave speed, and how it can be calculated. So speed is a fairly familiar concept. The greater something's speed, the faster it's moving, or the faster its position is changing. And it's expressed in distance per unit of time, so in things like kilometers per hour or meters per second. Now, with waves, speed really means the same thing. Remembering that a wave is just a disturbance that's moving through a medium or through space, the speed of a wave is how fast that disturbance moves through the medium. So what factors determine how fast a wave travels? You've recently used this simulation to see how features of a wave like amplitude and frequency have an effect on a wave's wavelength. In this video, we'll use the simulation to see what factors determine the wave's speed. So I'm going to do that by measuring how far waves with different amplitudes, frequencies, and traveling through different tension string, how far they travel in the same amount of time. So I'm going to measure how far they travel in 1 second. Now the waves that travel the furthest in that amount of time are traveling the fastest. So we'll see whether amplitude, frequency, or the tension of the string has an effect on the wave's speed. So I've got the speed set to slow motion to make this a bit easier, and I'm going to use the stopwatch on the left to time 1 second, and I'm going to use the vertical ruler to mark the furthest point that the wave gets to, so how far it travels in 1 second. Okay, here we go, and I'll stop it there. Well, that's pretty close. Now I'll just drag the ruler in, so that's as far as it reached in 1 second. Now I'm going to change, or I'll reset my timer, and I'm going to change the frequency. Let's drop it down to 1 hertz. So we had it on 1.5. So we'll see if having a lower frequency changes how far the wave travels. And a little bit more, stop it there. So you can see that the wave's traveled the same distance, even though it's got a different frequency. All right, let's try high frequency now. Let's go with 2 hertz. 2.01, and whoops, just need to start my timer. Okay, here we go. And in 1 second, you can see that it's still traveled the same distance. So it's still traveling at the same speed at 1.5 and 2 hertz. Let's just try one more at 3 hertz, and in just a touch over 1 second, you can see it's traveling at the same speed. So frequency is not making any difference to the speed. We'll just see if we can get that one right. Yeah, that's pretty good. So you can see that the speed of the wave isn't changed at all by the frequency. At the different frequencies we tested, it traveled the same distance in 1 second. So it's traveling at the same speed. We'll put frequency back to 1.5, and we'll try some different amplitudes. 0.3 centimeters, a fairly short wave. At just over 1 second, you can see it's traveled that far. So it's still traveling the same distance. Let's increase the amplitude to 1 centimeter. And in one second again, same distance. So it's still traveling at the same speed. Let's bump the amplitude all the way up. And probably no surprise, in 1 second, it's traveled the same distance. So amplitude also not having any effect on the speed of the wave. Let's just crank them both up. 1.25 centimeter amplitude, 3 hertz frequency, speed still the same. So amplitude, frequency aren't having any effect on the speed of the wave. I'm just going to put them back to where they started. So 0.75 centimeter amplitude, and a 1.5 hertz frequency, and we'll try the tension. So this is like how tight the string is being pulled. Now we had it set to high, but we're going to test it at a medium and a low frequency. A medium and a low tension as well. So high tension with those amplitude and frequency settings, it's the same distance, so it's still traveling at the same speed. Let's see if the medium tension makes a difference now. So we'll stop it at 1 second there. And you can see that distance that it's traveled is probably about half of what it traveled before. So it's moving much slower through a medium tension string. You might probably predict now, if we reduce the tension even more, you've probably guessed the wave's going to be even slower. So that's probably halved again the distance that it's traveled in 1 second. So it's the tension in the string, it's how tightly that string is pulled that's affecting the speed of the wave. So a wave's speed depends on what it's moving through. And if the medium changes, then the wave speed will change as well. So this applies to, like in the simulation, a wave moving through a string. If the string is pulled tighter, the wave will move faster. But all types of waves behave in the same way. Waves moving through deep water will move faster than waves moving through shallow water. Light, which is a type of wave, moves at different speeds through different mediums. And sound waves will travel through air at different speeds depending on the temperature. Now remember, in that test we didn't change the frequency, so the rate of the oscillations was exactly the same, and we just changed the tension. And we had 3 different speeds. So we had a high speed, a medium speed, and a low speed, corresponding to high, medium, and low tension. Now hopefully the other thing that you've noticed is that as well as the speed of these waves being different, they've also got a considerably different wavelength. The wavelength of the high speed wave is much longer than that of the medium speed and the low speed waves. And this brings us to a fundamental characteristic of waves, that their speed, their wavelength, and their frequency are all related. The relationship between these features is given in what's called the wave speed equation. The wave speed equation simply says that the speed of a wave is equal to its wavelength multiplied by its frequency. So speed, which is given the symbol v, is given in meters per second. Wavelength with the symbol lambda is measured in meters, and frequency with the symbol f is measured in hertz. So the equation can be written as v equals lambda times f. The equation can be used in 3 ways. You can calculate a wave's speed by multiplying its frequency and wavelength, or you can calculate a wave's frequency by dividing its speed by its wavelength, or you can calculate a wave's wavelength by dividing its speed by its frequency. So at this stage it's fair to ask, why do we need to know these things about waves? Well, as we'll soon learn in the next part of the topic, waves are used throughout almost every aspect of our lives. A huge array of modern technology and important scientific discoveries depend on the accurate measurement and calculations of wave speed, wavelength, and frequency. From our daily weather predictions to our understanding of the universe, tracking aircraft around the world, to designing the acoustic spaces used for music, speed cameras, global and interspace communications, the Wi-Fi that you're probably connected to right now, and the use of X-rays and other diagnostic imaging, all of these things rely on the accurate use and calculation of waves.